Hello everyone. My name is Mohammad Ahmed Mohsen and I'm a PhD student at Stanford University under Dr. John Shoffie's lab. And today I'm going to present you my project Deep Reinforcement Learning for 6G Network Optimization for my course Convex Optimization EE364B. So next generation wireless networks, they promise very high data rates, terahertz communication, very low latency, very less inference times, and very high reliability. But how do these promises get accomplished? There are some certain technologies that the 6G networks they promise, uh, and the issue is that we need to optimize all those technologies together so that they are integrated with each other so that we can get the maximum throughput under the minimum required energy constraints. So these technologies, I'll explain them one by one. The first is called a reconfigurable intelligent surface, which is an RIS. It's a programmable meta surface which consists of some elements which are passive elements, and these elements are used to direct the signals that are impinging on them towards the required users. So once a signal strikes uh, RIS, it will direct it towards the required user by changing the phase, the angle of the impinging signal towards the RIS. The second is called COMP, which is coordinated multi-point transmission. This is a technology which promises that all the base stations they will coordinate with each other so that once a base station is transmitting, the others they won't interfere, or either they'll send to different users or they'll use some different frequency bands. The third is the NOMA. NOMA is called non-orthogonal multiple access, which by its name, it's very clear that it's non-orthogonal means that the time and the frequency uh, domains are being utilized fully, but how are we then differentiating between different signals is through the power domain so that the user that is very far will be given some higher power and the user that is very near will be given some lower power, which makes sense as well. So NOMA wants to use all the frequency band and all the time band and just send the signals differentiated on the basis of their power. But then there is a factor that comes with NOMA, which is called alpha, or some in this paper we have used as rho, which we want to optimize so that how much power should the far user be given and how much power should the near user be given so that we can perform SIC very accurately. What is SIC? SIC stands for successive interference cancellation, so that you can decode the stronger user's signal first and then remove it from the total received signal so that you can get the weaker user signal automatically without the need to deal with all the noise and the inference. So this is just a brief summary of like what the 6G technology promises us. The next thing that I'll discuss is the system model that we go with and how do we optimize it using deep reinforcement learning. So the system model we are considering is two base stations with three number of users, and then an RAS that is on top of a UAV. So that UAV acts as a mobile base station that is placed strategically on places such that where there is a catastrophic network, where the users do not receive the the signals directly through the base station. So here our assumption is that two of the three users are a cell center users, so they directly receive the signal from the base station, and one user is a common cell edge user which does not receive the direct line of sight signal from the base stations. So it needs to get the signal from the base station to RIS and from RIS to the user itself. So this is the system model that uh, we assume for our work. Now, what I'll do is I'll explain some set of equations that we derive, then our objective that we optimize, and then some of the results that early results that we have, and then the future work that we will be doing. So first is the UAV trajectory constraint. So it keeps the drone that is mounted on the RAS inside the legal airspace and a safe distance from every obstacle. So we place some constraints on the UAV itself so that it does not go outside of the fly zone, and it does not strike any obstacles. So this Q of n is the horizontal UAV's horizontal coordinates. S is the authorized flight zones. C of m is the center of the mth no fly obstacle, and this R of safe is the mandated clearance from the obstacle M, and N and M are the number of time slots and the obstacle indices. So this is a UAV trajectory constraint. Then we have some phase shift model. So phase shift model is that, as I told you earlier, that we have a RAS, and RAS has a number of passive elements. So these elements, they want to change the phase shift of the signal such that uh, such that the signal is directed towards the intended user. So this phase shift matrix is actually a diagonal matrix e raised to power j phi of n, uh, where the j phi of n, they are programmable phase elements, L, at the time slot n, and they are given in radians, where L is the number of RAS elements, the total number of RAS elements. So this RAS, it actually results in a cascaded channel from the base station to the user. Why do we call it a cascaded channel? Because it's like first from the base station to the RAS, and the RAS will change the phase angles of the signal, and then from the RAS towards the intended signal user. So it's a cascaded channel from the base station to RAS, and then RAS towards the required user. So this equation gives us the resulting cascaded channel from the base station I to the user J. Uh, so this is actually the effective base station I to the user J channel via the RIS, and this HI of n, this is from the base station I to the RIS link G of J, which is the RIS to the user J link, and this is the phase shift matrix that we just used earlier. Now this is the transmit waveform and the power splitting. So as I told you earlier that NOMA, it uses actually power splitting to distinguish between the far user signal and the near user signal, because we are not distinguishing it in terms of the frequency, neither in terms of the time. So that in earlier systems, what happened was that either you have to transmit the signal in some time slot for the near user and the other time slot for the far user, or what you will do is you will have different frequencies for both the signals, but these time and frequencies are resources that we have to utilize very efficiently. So NOMA proposes to use all of the time and the frequency band, and just distinguish the users in terms of their power. So uh, this equation, what actually does is that xp of n is the signal sent by the base station p in the time slot n. Then we have this p of rho, which is base station's total power w, and then we have this underscore rho of p, which is the power fraction for the far users layer, and then we have this d of n, which is the unit power symbol for the common edge user, and similarly, we have this for the fire user as well. So this is a two user case. So we are subtracting it from 1 minus rho of p, because the rho of p sum can be maximum to 1. And we need to optimize it such that how much power should be allocated to one user and how much should be the power allocated to the second user. And how do we optimize it very efficiently? Now, this is the received signal at the fire user. It superposes all base station signal after the ARIA so that we can derive the user's SINR. So I'll explain this equation very, very quickly. So this YR of n is the received signal in the time slot n by the fire user. And now we have this P, which is equal to 1 to B, where B is the number of total base stations that we have. And this capital sigma of P is the cascaded base station from row to RAS and from RAS to fire users channel gain. X of P of N, which is the base station's transmit signal that we have already shown you earlier as well. This, and then we have this, which is called the AWGN, additive white Gaussian noise, and from this received signal, this received signal at the far user, we extract the signal to noise ratio, And this is the received signal at the far user. So as I told you earlier, what Noma does is that Noma wants to extract stronger users signal first and then the weaker user signal. So the concept in Noma is that the fire user is allocated more power because it's a fire user. So once you receive the total signal, the fire user is actually a more stronger signal. So you can see this is the signal, and the other user, one minus rho, the other user is acting as the noise along with the AWGN. So you extract the received signal for the fire user. Similarly, for the near user, what we have, as you can see that this is the received signal for the near user. This is the composite, which means direct plus RAS channel base station to the near user. The near user will always also have a signal that comes from the RAS towards the near user, but it's a minimal signal because the near user is already receiving the line of sight path from the base station to the RAS itself. And then this is the interference from the, so what's happening is that we assume that the coordinated multi-point transmission is only for the far user. So the center users are receiving interference from other base stations as well, and this is this term. And after SAC, after successive interference cancellation, this is what you are, what you get as for the received SNR. So what's the total data rate that we want to get is log 1 plus SNR for the far user, for the near user, and 1 plus SNR for the far user as well. And this is the total rate that we achieve, and we want to actually maximize the total spectral efficiency or the total sum rate. And how do we maximize it? There are some parameters that we are optimizing, which is the phase shift of the RAS. This is the first thing. The second is the NOMA power allocation factors. The third is the total transmit power that we want to optimize. And then the fourth is the UAV trajectory, like where do we optimally place the UAV to get the best throughput and the back and the maximum total data rate that you can see here as well. There's a total data rate which is given, which is the sum of the far user data rates as well as the near user data rates. They are subject to some constraints, uh, which we have, which I told you earlier. This is the UAV. These are the UAV safety constraints. It should not be in the no-fly zone. It should be far. It should be keeping a far safe distance from the obstacles. Then this is from minus pi to pi are the phase shift matrices low, so that RES elements can only have a phase shift from minus pi to pi, which is actually 0 to 360 if you check it. So this is the minimum required. The data rate for the far user, for the center user, should be greater than the minimum required data rate, and similarly for the far user, the data rate should be greater than some minimum required data rate. This is the NOMA power allocation factor, and this is the total transmit power of the base station. So these are all some constraints that we keep while we want to maximize this. We use a multi-output hybrid proximal policy optimization PPO, because there are some discrete and continuous variables. Both discrete is something like the UAV positions and everything, and the continuous are like these NOMA factors or this transmit powers, these data rates, or they can be continuous. So we assume a hybrid PPO policy. So these are some of the results. You can see that the exhaustive search is an upper bound, because exhaustive search actually exhausts all the resources to check uh, every combination that can achieve the maximum rate. It takes a lot of time to run. But then, because wireless networks cannot afford this, they need to work very fast on inference times. And RL agents, they have a single neural feed forward network, so they can be very fast at inference times. So we have this hybrid PPO optimal phase shifts, as well as I tried with the random phase shifts as well, that keeping all other constraints the same. If I just keep random phase shifts of the RAS but optimize the rest of them, so what's the difference between the two? So you can see there's a total sum rate difference between these. And similarly, this is from the number of RAS elements that you can see, and this is the total transmit power. And we can see that as we increase the transmit power, the sum rate of course increases. But after the exhaustive search, if we have the optimal phase shifts, then we can more efficiently utilize the power of reconfigurable intelligent surfaces rather than having a random phase shift that you can see here. So this was my course project, and for the future and for the final report, I'm looking into uh, checking how is the UAV's trajectory being optimized and how are other variables being optimized, how is the reward converging, what are the different types of rewards that I can try, is there any different agent that I can try, and yep, that's it. Thank you everyone. uh, so